4 light-years away sits a star almost identical to our Sun. For decades, astronomers desperately wanted to know if planets orbited it. Every attempt failed. The star was too bright, its companion star too close. The target moved too fast across our sky. Then the James Webb Space Telescope pointed its golden mirrors toward Alpha Centauri and captured something that made scientists gasp. A faint dot of light appeared beside the star, then vanished. Follow-up observations found nothing. The planet, if it exists, had disappeared. What JWST discovered in our closest stellar neighborhood defies everything we expected about finding worlds beyond our solar system. If you want to witness the most significant detection in exoplanet history, hit that like button and subscribe. Let's begin. Alpha Centauri is not just another star system scattered across the night sky. It represents humanity's closest stellar neighbor, the first stop on any conceivable interstellar journey, the cosmic front porch of our solar system. For more than 70 years, astronomers have obsessed over a single haunting question. Does it have planets? The answer seemed perpetually out of reach. Not because technology did not exist to find worlds orbiting other stars. Scientists have discovered nearly 6,000 exoplanets using various detection methods refined over decades of innovation. Gravitational wobbles reveal massive planets tugging on their host stars. Periodic dimming exposes worlds crossing stellar faces during transit events. Direct imaging captures the faint glow of young, hot planets orbiting distant suns. The problem was Alpha Centauri itself. This star system breaks every rule astronomers developed for hunting planets around other stars. Its unique characteristics transform what should be the easiest target in the sky into perhaps the most challenging observation ever attempted. Confirmed measurements reveal that Alpha Centauri sits just 4.37 light-years from Earth. In cosmic terms, this distance qualifies as spitting distance. Light leaving this system tonight will reach your eyes in less than 4.5 years. A photon departing Alpha Centauri when you started high school arrives before you finish college. Compare this proximity to typical exoplanet host stars, which lie hundreds or thousands of light-years distant. The nearest confirmed transiting exoplanets orbit stars dozens of times farther than Alpha Centauri. Most directly imaged worlds circle stellar furnaces located hundreds of light-years away. Alpha Centauri practically shares our cosmic neighborhood. This closeness should make planetary detection trivially easy. Nearby objects appear brighter and larger than distant ones. The same planet that vanishes into stellar glare at 100 light-years might shine clearly at 4 light-years. Proximity should provide overwhelming advantages for planet hunters targeting our nearest stellar neighbor. But proximity creates problems rather than solutions when it comes to Alpha Centauri. The system shines with blinding intensity that overwhelms the sensitive instruments designed to detect faint planetary signals. Imagine trying to photograph a firefly hovering next to a searchlight. The searchlight's glare drowns everything in its vicinity. Alpha Centauri A, the largest star in the triple system, ranks as the third brightest star visible from Earth's surface. Only Sirius and Canopus outshine this blazing stellar furnace. On clear nights in the southern hemisphere, Alpha Centauri dominates the constellation Centaurus, with yellow-white brilliance that ancient navigators used to chart their courses across unknown oceans. Its companion, Alpha Centauri B, orbits close enough to create additional complications that compound the brightness problem. The two sun-like stars circle their common center of mass every 80 years, approaching within 11 astronomical units at closest passage, and separating to 36 astronomical units at maximum distance. During observations, the companion floods detectors with contaminating light that obscures any faint planetary signals around the primary star. A distant third member called Proxima Centauri lurks roughly 13,000 astronomical units from the central binary pair. This dim red dwarf barely qualifies as a star, shining with less than 1% of solar luminosity. Proxima orbits so far from Alpha Centauri A and B that it takes more than 500,000 years to complete a single circuit around the system's center of mass. Scientists already confirmed that Proxima Centauri hosts at least 2 planets, with a possible third candidate still under investigation. These worlds orbit a star so fundamentally different from our Sun that comparing them to Earth makes little scientific sense. Red dwarf planets face violent stellar flares that can strip atmospheres within geological timescales. Tidal locking turns one hemisphere toward eternal day, while the other experiences endless frozen night. The habitable zones around red dwarfs lie so close to their host stars that gravitational forces lock planetary rotation to orbital periods. Finding planets around the Sun-like stars Alpha Centauri A and B would carry far more profound implications. These stellar furnaces resemble our own Sun in nearly every measurable characteristic. Their masses, radii, temperatures, and ages match solar values within reasonable margins. Planets orbiting these stars would experience conditions genuinely comparable to what Earth receives from the Sun, but detecting such worlds requires technology capable of separating faint planetary light from overwhelming stellar glare. The brightness ratio between a Sun-like star and a Saturn-mass planet exceeds 10,000 to 1. Finding that planet requires instruments sensitive enough to detect signals 10,000 times fainter than the blinding stellar background. The James Webb Space Telescope was never designed for this observation. Engineers built JWST to study the most distant galaxies in the observable universe. Objects so far away they appear as faint smudges, even through the most powerful instruments ever constructed. The telescope's detectors were optimized for capturing ancient photons that traveled billions of years across cosmic space before reaching the golden mirrors orbiting at Lagrange point 2. Pointing this exquisitely sensitive instrument at one of the brightest objects in the night sky seems counterintuitive at best, like using a submarine to climb a mountain, like wielding a scalpel to fell a redwood. The technical challenges appeared insurmountable to many astronomers who initially dismissed the entire concept as impractical wishful thinking. The telescope cost approximately $10 billion and took more than 20 years to design, build, test, and deploy. Nobody wanted to risk damaging priceless detectors by pointing them at stellar furnaces bright enough to potentially cause permanent harm. The conservative approach suggested avoiding bright targets entirely and focusing on the distant universe JWST was designed to explore. But Charles Beichmann refused to accept conservative approaches. This veteran astronomer from NASA's Jet Propulsion Laboratory and the NASA Exoplanet Science Institute had dreamed of detecting planets around Alpha Centauri since before JWST even launched. He assembled a team of researchers willing to attempt what others considered impossible. His proposal used JWST's mid-infrared instrument, called MIRI, to search for thermal emissions from potential planets around Alpha Centauri A. The concept relied on detecting heat rather than reflected starlight. Planets absorb radiation from their host stars and re-emit this energy as infrared warmth. A world orbiting in the habitable zone of Alpha Centauri A would reach temperatures between 200 and 350 Kelvin, cool enough to emit mid-infrared radiation at wavelengths where MIRI achieves peak sensitivity. The physics favors this approach for mature planetary systems. Young planets glow brightly from residual formation heat that has not yet radiated into space. These hot worlds emit strongly in near-infrared wavelengths accessible to many telescopes. But older planets that formed billions of years ago have cooled considerably. Their thermal emissions peak at longer mid-infrared wavelengths that only specialized instruments can detect. Alpha Centauri A has existed for approximately 5 billion years, roughly the same age as our Sun. Any planets orbiting this mature star would have long since lost their formation heat. They would shine only through absorbed and re-emitted stellar radiation at the frigid temperatures appropriate for their orbital distances. MIRI's 15.5 micrometer filter offered the best chance of capturing these faint thermal signals. But detecting planetary glow requires blocking the overwhelming glare from the host star. MIRI includes a coronagraph designed for exactly this purpose. This specialized instrument places a physical mask called a 4-quadrant phase mask over the star's position on the detector. The mask creates an artificial eclipse that suppresses stellar light while allowing fainter objects at slightly different positions to remain visible. Coronagraphs work through destructive interference. Light waves from the blocked star combine in ways that cancel each other out, reducing brightness by factors of hundreds or thousands. Meanwhile, light from objects positioned slightly away from the mask center passes through relatively unaffected. The contrast between suppressed stellar light and preserved planetary light makes detection possible. The coronagraph performs beautifully for most stellar targets observed by JWST. Stars at typical exoplanet hunting distances present manageable brightness levels that fall well within instrument specifications. Standard target acquisition procedures lock onto these stars without difficulty using normal operational modes. Observations proceed according to established protocols refined through hundreds of successful campaigns. Alpha Centauri shattered every assumption underlying these standard procedures. The system presented unique complications that threatened to ruin any observation attempt before it could even begin. First and most fundamentally, the star moves. Alpha Centauri possesses one of the largest proper motions of any naked-eye star in the sky. It races across the celestial sphere at approximately 3.7 arcseconds per year, covering angular distances visible to the unaided eye over human lifetimes. This motion sounds tiny in absolute terms, but represents significant displacement during the precise observations JWST requires. The telescope must continuously adjust its pointing to keep the star centered precisely behind the coronagraphic mask. Errors of even 10 milliarcseconds degrade coronagraph performance and allow stellar light to leak around the mask edges. Alpha Centauri's rapid proper motion demanded tracking precision beyond anything attempted with previous JWST observations. Second, the binary companion creates observational chaos that no single coronagraph can solve. Alpha Centauri B orbits close enough during current decades that its brilliant light floods the MIRI detector, scattering contamination across the entire field of view. No coronagraph in existence can simultaneously block two bright stars positioned at different locations. The companion's presence meant that even perfect coronagraphic suppression of Alpha Centauri A would leave massive contamination from its stellar sibling. Third, Alpha Centauri A is simply too bright for standard JWST operations. Target acquisition procedures that work flawlessly for normal stars would completely overwhelm the sensitive detectors when pointed at this blazing furnace. The telescope's fine guidance sensors were not designed to lock onto objects this luminous. Standard brightness limits existed specifically to prevent detector damage from exactly this type of observation. Fourth, the galactic background creates identification, confusion that plagues every observation. Alpha Centauri lies directly in the plane of the Milky Way, where thousands of faint background stars crowd every field of view. Any detected signal must be carefully distinguished from these unrelated sources. A faint point of light might be a planet orbiting Alpha Centauri A, or might be a distant galaxy, billions of light years away, that happens to align with the nearby stellar system. The operations team at the Space Telescope Science Institute faced a seemingly impossible task. They needed to develop custom observing sequences that had never been attempted with JWST. Standard procedures would not function. Every aspect of the observation required innovation, creativity, and willingness to push the telescope beyond its design specifications. The solution emerged through months of careful planning and simulation. The team developed a technique called blind offsetting that bypassed the brightness limitations, preventing direct target acquisition. Instead of pointing at Alpha Centauri A directly, the telescope would first acquire a nearby reference star of manageable brightness. They selected Epsilon Muscae, a red giant star located approximately 330 light-years from Earth in the constellation Musca. This distant stellar furnace provides suitable brightness for standard acquisition procedures. The telescope's guidance systems could lock onto Epsilon Muscae without difficulty using normal operational modes. From this reference position, the telescope would perform a precisely calculated offset to position Alpha Centauri A behind the coronagraphic mask without ever directly pointing at the target. This blind maneuver required knowing the exact positions of both stars to accuracies measured in milliarc seconds. The slightest error would place Alpha Centauri A off-center from the mask, allowing stellar light to flood the detector and ruin the observation. The calculations incorporated Alpha Centauri's rapid proper motion and significant parallax. At a distance of only 1.34 parsecs, the star's apparent position shifts by 750 milliarc seconds as Earth orbits the Sun. This parallax motion creates seasonal variations that must be precisely accounted for when calculating offset coordinates. Every observation required fresh calculations, incorporating the exact date and time of execution. Coordinates valid in January would place the star in the wrong position by March. The team developed software pipelines that automatically computed updated offset values based on observation scheduling. Nothing could be assumed constant when targeting a star that moves measurably against the celestial background. The first observation attempts occurred in 2023. They failed completely. Technical difficulties rendered the data entirely unusable. The telescope struggled to maintain precise positioning while simultaneously compensating for target motion and extreme brightness. Coronagraph performance degraded below levels required for planet detection. The contamination from Alpha Centauri B scattered everywhere. Initial failure would have discouraged many research teams. The difficulties seemed to confirm what skeptics predicted from the beginning. Alpha Centauri was simply too challenging for JWST to observe productively. The telescope should return to its designed mission, studying distant galaxies, rather than attempting impossible planetary detections. But Beichmann's team refused to abandon their goal. They regrouped, analyzed what went wrong, and developed improved strategies addressing each failure mode. They modified pointing procedures to achieve better centering accuracy. They developed new data reduction techniques specifically designed to handle contamination from the binary companion. They tested everything through exhaustive simulations before attempting another observation. In mid-2024, they implemented their refined approach. Test observations demonstrated that the modifications worked. JWST could finally observe the impossible target with sensitivity approaching theoretical limits. The team requested and received approval for a full observation campaign. In August 2024, the telescope executed 3 long observation sequences pointed at Alpha Centauri A. Each exposure lasted hours, as the coronagraph blocked stellar light while detectors collected whatever faint signals emerged from surrounding space. The team watched data stream back from Lagrange Point 2 with a mixture of anticipation and anxiety. The raw images showed exactly what astronomers expected from such a challenging observation. A chaotic mess of light contamination, diffraction patterns, and detector artifacts covered the frames. Alpha Centauri B blazed near the top of each image, its scattered light creating bright streaks and halos extending across the entire field of view. The coronagraph produced complex ripple patterns as stellar light bent around mask edges through diffraction. No human eye could identify anything meaningful in these raw data products. The images appeared as abstract noise patterns with no obvious astronomical information content. Extracting useful science required sophisticated image processing techniques developed specifically for high-contrast coronagraphic observations. The team employed a method called reference star differential imaging. They observed other stars using identical coronagraphic configurations to create templates showing how the instrument behaves when no planet exists in the field. Subtracting these reference templates from Alpha Centauri data removed systematic patterns arising from optical effects while preserving genuine astronomical signals that appeared only around the target star. Additional algorithms called principal component analysis and Kahunen-Loew image processing stripped away remaining contamination sources. These mathematical techniques identify and remove correlated noise patterns that reference subtraction alone cannot eliminate. Layer by layer, component by component, the data reduction process revealed what lay hidden beneath the stellar glare. What emerged from this painstaking analysis shocked everyone involved. At a separation of approximately 1.5 arcseconds from Alpha Centauri A, a faint point of light appeared in the fully processed images. This object, designated S1 by the Discovery team, shone more than 10,000 times fainter than its brilliant host star. Its angular position placed it roughly 2 astronomical units from Alpha Centauri A. The detection achieved statistical significance of 5.5 sigma. This technical measure indicates the probability of the observed signal arising from random noise, rather than a genuine astronomical source. At 5.5 sigma, that probability drops below 1 in 10 million. Random fluctuations essentially never produce signals this strong. Something real had been detected beside our nearest Sun-like stellar neighbour. Rigorous testing followed immediately. The team needed to eliminate every possible alternative explanation before claiming a planetary discovery. Extraordinary claims require extraordinary evidence. A planet around Alpha Centauri would rank among the most significant discoveries in exoplanet history. The evidence had to withstand the most skeptical scrutiny imaginable. Could S1 be a distant background galaxy masquerading as a nearby planet? Compact galaxies occasionally appear as unresolved points of light, even through the most powerful telescopes. The team cross-referenced their detection position against every astronomical catalogue containing known background sources. Nothing matched. No previously identified object occupied the detected location. Could S1 be a foreground object like an asteroid passing between JWST and Alpha Centauri during observations? Solar system bodies occasionally drift through fields of view during long exposures. Motion analysis examined whether the detected signal shifted position during the observation period. It remained stationary relative to Alpha Centauri A, ruling out nearby moving objects. Could S1 be an instrumental artifact created by complex optical interactions within the coronagraph? Sophisticated instruments sometimes produce spurious signals through mechanisms unrelated to actual astronomical sources. The team performed exhaustive injection recovery tests, inserting simulated planetary signals into raw data and verifying they could distinguish genuine detections from processing artifacts. Real signals behave differently than artifacts in subtle but measurable ways. S1 passed every test designed to expose false positives. The August 2024 observation appeared to capture a planet candidate orbiting our nearest Sun-like stellar neighbour. If confirmed through additional observations, this detection would rank among the most significant discoveries in the history of planetary science. Decades of searching might finally have succeeded, but the team recognized that a single observation epoch could not provide definitive confirmation. True planets orbit their host stars in predictable patterns governed by gravitational physics. Their positions change over time according to Kepler's laws. Confirming S1 as a genuine planet rather than some exotic artifact required observing it at multiple epochs and watching it move along a consistent orbital path. The Space Telescope Science Institute granted directors discretionary time for urgent follow-up observations. This precious resource provides rapid response capability for scientifically critical targets that cannot wait for normal proposal cycles. The Alpha Centauri planet candidate qualified without question for this expedited treatment. 2 additional observation campaigns were scheduled for early 2025. February and April observations would capture the Alpha Centauri A system, using techniques identical to the August discovery data. If S1 represented a genuine planet, it should appear at different positions consistent with orbital motion between the observing epochs. The amount and direction of movement would constrain the orbital period and geometry. The scientific community held its collective breath waiting for results. Rumors circulated through astronomical conferences and online forums. The closest Sun-like star to Earth might actually host a directly imaged planet. A cosmic neighbor that philosophers and scientists had wondered about for centuries might finally reveal its planetary family. The implications extended far beyond simple detection statistics and discovery credits. Alpha Centauri A resembles our Sun in nearly every measurable way. Its mass exceeds solar mass by only approximately 10%. Its radius matches solar dimensions almost exactly. Its surface temperature of 5,790 Kelvin falls within 200 degrees of the Sun's 5,772 Kelvin photosphere. Its luminosity exceeds solar output by roughly 50%. Finding a planet around this genuine solar twin would provide unprecedented opportunities for comparative planetary science. Every other directly imaged exoplanet orbits young, hot stars vastly different from our Sun. These juvenile stellar systems reveal how planets behave during their earliest evolutionary phases, but they tell us little about mature planetary systems like our own solar neighborhood. A planet around Alpha Centauri A would be heated by genuinely sun-like radiation for the first time in direct imaging history. Scientists could study how planetary atmospheres respond to solar-type stellar spectra. They could search for atmospheric signatures that might indicate geological activity or even biological processes. The preliminary analysis from August data suggested S1 possessed an effective temperature around 225 Kelvin, approximately negative 48 degrees Celsius. This frigid temperature placed the object near the outer boundary of Alpha Centauri A's habitable zone, the circumstellar region where liquid water could theoretically persist on rocky planetary surfaces. Of course, S1 appeared to be a gas giant rather than a rocky world. Mass estimates based on brightness and temperature suggested roughly 90 to 150 Earth masses, comparable to Saturn's 95 Earth mass bulk. Gas giants cannot support liquid water oceans or the biological processes humans associate with life. Their crushing atmospheric pressures and lack of solid surfaces preclude the chemistry underlying terrestrial biology. But gas giants frequently host extensive moon systems. Saturn alone possesses more than 270 known natural satellites. These moons range from irregular captured asteroids to world-sized bodies with complex geology and atmospheric systems. Titan maintains a dense nitrogen atmosphere thicker than Earth's. Enceladus conceals a global subsurface ocean beneath its icy crust. Either moon might harbour conditions suitable for microbial life. A Saturn-mass planet in the habitable zone of our nearest Sun-like star could potentially host moons where liquid water exists and biological chemistry operates. The possibility transformed idle scientific speculation into urgent observational priority. Finding evidence for such a system would reshape humanity's understanding of our cosmic neighborhood. The August detection also challenged theoretical models predicting how planets form and survive in binary stellar systems. Alpha Centauri A and B orbit each other at distances that should disrupt planetary formation processes. Computer simulations consistently showed protoplanetary disk material being stripped away before it could coalesce into worlds. Stable planetary orbits existed only in restricted zones close to each star or far from the binary center of mass. Yet S1 apparently occupied exactly the marginal stability region where theory predicted planets might barely survive. If confirmed, the detection would force theorists to reconsider how worlds form and evolve amid the gravitational chaos of binary stellar environments. Perhaps planets are more resilient than simulations suggested. Perhaps formation mechanisms exist that current models fail to capture, but confirmation required additional observations demonstrating orbital motion consistent with gravitational binding to Alpha Centauri A. The February and April 2025 campaigns would provide critical data for distinguishing genuine planetary detections from instrumental artifacts or background contamination. What nobody expected was the result those follow-up observations would produce. The planet candidate that generated such excitement in August would behave in ways that defied simple explanation. What the telescope found in early 2025 created a mystery that continues puzzling astronomers and challenging assumptions about what JWST actually detected in the Alpha Centauri system. The February 2025 observations proceeded flawlessly from a technical standpoint. Every system aboard the James Webb Space Telescope performed exactly as designed. The complex blind offset maneuver placed Alpha Centauri A precisely behind the coronagraphic mask. Detectors collected photons for hours while the telescope maintained rock-steady pointing against the cosmic background. Data streamed back to Earth at the speed of light, crossing the million miles between Lagrange Point 2 and ground stations within seconds. Eager scientists waited at their terminals, ready to process images that might confirm the most significant planetary discovery in decades. The August detection had tantalized the astronomical community for months. Now confirmation seemed within reach. The analysis pipeline activated immediately upon data arrival. Terabytes of raw detector readouts fed into processing algorithms refined through countless previous observations. Reference star subtraction removed systematic coronagraphic artifacts that would otherwise contaminate the field. Principal component analysis identified and stripped away correlated noise patterns lurking beneath the primary signal. The same techniques that unveiled S1 in August ground through the February data with mechanical precision. Scientists watched as layer after layer of contamination peeled away, revealing whatever astronomical signals lay hidden beneath the stellar glare. The processing that had previously exposed a planet candidate now searched for that same object at its predicted new position. Nothing appeared. The region where S1 had blazed with 5.5 sigma statistical significance in August showed only empty space in February. No strong detection emerged from the noise. No marginal signal hinted at planetary presence. Nothing but random fluctuations occupied the space where a Saturn mass world should have been clearly visible. Scientists double-checked their analysis. Perhaps a processing error had corrupted the results. Perhaps the data required different reduction parameters optimized for current observing conditions. They reran the pipeline with modified settings. They tried alternative algorithms. They examined the raw data directly for any hint of signal that processing might have inadvertently removed. Every approach produced identical conclusions. The February observations contained no detectable planet around Alpha Centauri A at any position within the coronagraph's sensitive field of view. S1 had vanished. The April 2025 observations offered another chance. Perhaps February represented an unlucky observation epoch where some transient condition degraded sensitivity. Perhaps the planet had moved to an unfavorable position that would shift by April. 2 months of orbital motion might place S1 back within detectable range. April data arrived and underwent identical scrutiny. The processing pipeline churned through fresh observations, searching for any trace of the August discovery. Scientists examined every corner of the field with desperate thoroughness. More empty fields, more null detections. The candidate planet had completely disappeared. Whatever JWST detected in August 2024 no longer revealed itself to the most powerful space telescope ever constructed. Aniket Sanghi, a doctoral student at the California Institute of Technology and co-first author on the discovery papers, described the situation with a phrase that captured the scientific community's bewilderment. They faced the case of a disappearing planet. The object that generated such excitement and anticipation seemed to have evaporated into the cosmic void between observation epochs. This outcome demanded explanation. Planets do not simply vanish. Gravitationally bound objects, orbiting stars, follow predictable paths, governed by Newton's laws, and Einstein's refinements. If S1 represented a genuine world circling Alpha Centauri A, it should appear somewhere in every observation, even if that position changed according to orbital motion. 3 distinct possibilities emerged to account for the missing signal. Each explanation carried profound implications for understanding what JWST actually detected during those August observations. Each demanded careful evaluation against all available evidence. The first possibility suggested the most deflating conclusion. Perhaps S1 was never real in the first place. Despite passing every statistical test and artifact rejection criterion the team could devise, the August detection might represent an extraordinarily improbable fluctuation in detector noise that happened to mimic a genuine astronomical source. Random processes occasionally produce patterns that appear significant. Flip a coin enough times and eventually you will observe sequences that seem impossibly unlikely. Electronic detectors measuring faint signals experience quantum fluctuations that create spurious readings. Perhaps August 2024 witnessed exactly such a statistical fluke masquerading as a planetary detection. This explanation seemed deeply unlikely given the strength of the original signal. 5.5 sigma significance means the probability of random noise creating such a strong false positive drops below 1 in 10 million. Scientists designed detection thresholds specifically to exclude random fluctuations at these improbability levels. Claiming noise produced the August signal required accepting extraordinarily bad luck. Furthermore, the team had tested the detection extensively across different data subsets. They split the August observations into independent portions and analyzed each separately. Both halves reproduced the S1 signal at consistent positions and brightnesses. Genuine noise fluctuations rarely behave so consistently across independent data samples, but statistics never completely eliminate false positive possibilities. 1 in 10 million events do occasionally occur. The universe contains enough observations that even extraordinarily rare coincidences must happen somewhere. Perhaps Alpha Centauri became the unlucky target, where random chance conspired to create an illusory planet. The second possibility involved contamination from unknown background sources. Astronomical images capture everything along the line of sight between telescope and target. Distant galaxies, billions of light-years away, appear as faint points of light that can masquerade as nearby planets, until careful analysis reveals their true nature. Perhaps some previously uncatalogued cosmic source happened to occupy the detected position during August observations. A compact, distant galaxy or an extremely faint background star might have created the signal attributed to a planet. If this background object possessed significant proper motion of its own, it might have drifted away from the detection position by February, explaining both the initial signal and subsequent non-detections. The research team exhaustively investigated this scenario. They examined data from the Gaia spacecraft, which has precisely measured positions and motions for nearly 2 billion stars throughout the Milky Way galaxy. No stellar source appeared anywhere near the S1 detection location at any epoch covered by Gaia observations. They searched archival images from multiple ground-based and space-based telescopes spanning decades of observations. Deep exposures from various instruments at different wavelengths revealed no background object consistent with the detected brightness and position. The region around Alpha Centauri A appeared genuinely empty of contaminating sources capable of producing the August signal. They also analyzed the spectral characteristics of the detected light. Background galaxies typically show different color signatures than cool planetary atmospheres. The wavelength distribution of S1's emission remained consistent with a thermally emitting planet rather than a distant galaxy. Every test designed to expose background contamination came back negative. The third possibility offered the most scientifically intriguing explanation for the disappearing signal. S1 might be a completely genuine planet that moved beyond detection limits between observation epochs through simple orbital mechanics. Understanding why this explanation works requires examining how coronagraphic sensitivity varies across the field of view. These instruments do not provide uniform detection capability at all positions around a block star. Physics conspires to make some regions highly sensitive, while rendering others effectively blind. Coronagraphic masks suppress starlight by covering the central stellar image on the detector. The mask creates an artificial eclipse that blocks the overwhelming glare, allowing fainter nearby objects to become visible. But diffraction fundamentally limits how completely any physical mask can block electromagnetic radiation. Light waves bend around edges through a phenomenon called diffraction. When starlight encounters coronagraph mask boundaries, some fraction bends around those edges rather than being blocked. This diffracted light creates complex patterns of residual brightness, extending outward from the mask's stellar position. Close to the star, diffracted light overwhelms any planetary signals trying to emerge from the glare. Only at certain angular separations does sensitivity reach levels capable of detecting the extreme contrast ratios required for planet imaging. Too close to the star, and diffracted contamination dominates. Too far from the star, and the planet's signal becomes too faint against detector noise. A sweet spot exists where detection becomes possible, but that sweet spot is narrower than many astronomers initially appreciated. Additionally, coronagraph sensitivity varies dramatically with position angle around the blocked star. The four-quadrant phase mask used by MIRI creates different suppression levels in different directions, depending on how mask geometry interacts with the telescope's optical structures. Some position angles achieve excellent contrast, while others remain hopelessly contaminated. Planets orbiting at unfavorable position angles become temporarily invisible, even if they remain at separations where detection should theoretically be possible. A world might shine clearly when positioned along one direction from its star, then disappear entirely when orbital motion carries it to an unfavorable angle just a few months later. If S1 follows an elliptical orbit rather than a circular path, its distance from Alpha Centauri changes continuously throughout its year. At some orbital phases, the planet approaches closer to the star, where coronagraphic sensitivity degrades below detection thresholds. At other phases, it might pass in front of or behind the star from Earth's viewing perspective, hiding the planet through simple geometric alignment. Either situation would cause a genuine planet to temporarily disappear from JWST images, despite remaining gravitationally bound to its host star. The February and April non-detections might not indicate that S1 never existed. They might simply mean the planet had moved to an unfavorable orbital position where current technology cannot see it. The research team tested this hypothesis through sophisticated orbital simulations, exploring every possible planetary path consistent with available observations. They generated millions of simulated orbits with varying periods, eccentricities, inclinations, and orientations. Each simulated planet had to satisfy physical constraints, including gravitational stability in the presence of Alpha Centauri B. The simulations also incorporated tantalizing information from an earlier observation that had been nearly forgotten in the excitement surrounding the JWST detection. In 2019, astronomers using the European Southern Observatory's Very Large Telescope in Chile captured a faint signal near Alpha Centauri A that hinted at possible planetary presence. This ground-based detection, designated C1, appeared at approximately 1.1 astronomical units from the host star. The signal emerged from observations using a mid-infrared instrument called NEAR, specifically designed for high-contrast imaging of nearby stellar systems. But ground-based telescopes face severe limitations that space observatories avoid. Earth's atmosphere constantly churns and distorts incoming light through temperature variations and turbulent air motion. This atmospheric seeing blurs stellar images and creates spurious signals that can mimic planetary detections. Adaptive optic systems partially correct these distortions, but cannot eliminate them completely. Ground-based coronagraphy operates at significantly lower sensitivity than space-based alternatives. The C1 detection never achieved confirmation status because of these atmospheric limitations. The signal appeared marginally in processed images, but could not be definitively distinguished from residual atmospheric artifacts. Most astronomers filed it away as an interesting hint requiring better data rather than a confirmed planetary detection. But what if C1 and S1 represented the same object observed at different orbital phases 6 years apart? A planet on an eccentric orbit would appear at different distances from its host star depending on when observations occurred. The 2019 ground detection and 2024 space detection might both be capturing brief glimpses of a single world moving along an elongated orbital path. If this hypothesis held, combining both detections would dramatically constrain possible orbits. A planet must follow a path that places it at approximately 1.1 astronomical units during 2019 observations and approximately 2 astronomical units during August 2024. The orbit must then carry the planet somewhere undetectable during February and April 2025. The team explored whether any physically plausible orbit could satisfy all these constraints simultaneously. The computational challenge was immense. Millions of orbital configurations required testing against multiple detection and non-detection epochs, while ensuring long-term gravitational stability within the Alpha Centauri binary system. The results that emerged from these calculations stunned the research team. Computer models found that 52% of gravitationally stable orbits, fitting the combined S1 and C1 astrometric positions, would naturally produce non-detections in both February and April 2025. These orbits carried the planet to regions where JWST's coronagraphic sensitivity dropped below thresholds required for detection during exactly those months. This statistical finding transformed the interpretation of non-detection results entirely. Rather than contradicting the planetary hypothesis, the February and April null observations actually remained consistent with S1's existence. The disappearing planet was not violating physical laws. It was behaving exactly as orbital mechanics predicted for more than half of all possible configurations. A genuine planet following certain orbital paths would be visible in August 2024, invisible in early 2025, and visible again at some future date when its orbit carried it back to favorable positions. The absence of detection during follow-up observations provided no evidence against the planet's reality. Statistical analysis showed non-detection was more probable than detection given the range of allowed orbits. The surviving orbital solutions painted a picture of an unusual and scientifically fascinating planetary system. S1 appears to follow a significantly eccentric orbit, where its distance from Alpha Centauri A varies dramatically throughout each orbital period. Current estimates suggest eccentricity values around 0.4, meaning the planet's closest approach distance is only about 60% of its maximum separation. Compare this to planets in our solar system. Earth follows an almost perfectly circular orbit, with eccentricity below 2%. Even Mars, with its noticeably elliptical path, reaches only 9% eccentricity. Mercury holds the record among major planets at 21% eccentricity. S1's estimated 40% eccentricity exceeds anything in our planetary neighborhood, except for certain dwarf planets and comets. The orbital period falls somewhere between 2 and 3 Earth years, based on current constraints. At closest approach, called perihelion, the planet passes within roughly 1 astronomical unit of Alpha Centauri A, similar to Earth's distance from the Sun. At maximum separation, called aphelion, it retreats to nearly 2 astronomical units, approaching the orbital radius of Mars. This wide swing through different stellar distances creates the visibility pattern that explains both detections and non-detections. When S1 approaches perihelion, it moves too close to the star for coronagraphic detection. The planet effectively hides in the stellar glare during this portion of its orbit. When it retreats toward aphelion, it emerges into regions where MIRI achieves sufficient sensitivity for detection. The August 2024 observation apparently captured S1 near aphelion, where it remained visible against the suppressed stellar background. By February and April 2025, the planet had moved toward perihelion, where coronagraph performance degraded below detection capability. The planet did not vanish, it simply moved to an orbital phase where current technology cannot see it. Perhaps the most surprising aspect of the derived orbital parameters involves inclination relative to the Alpha Centauri binary orbital plane. The two bright stars orbit their common center of mass along a well-determined path inclined about 79 degrees from our line of sight. Planets forming from material in the original protoplanetary disk should share this orbital orientation. But S1 appears to orbit at roughly 50 degrees inclination relative to the binary plane. The planet's path tilts dramatically compared to the configuration shared by Alpha Centauri A and B. This misalignment suggests either highly unusual formation conditions or subsequent gravitational evolution that tilted an initially aligned orbit through some dynamical process. Formation models generally predict that planets inherit angular momentum orientations from their parent protoplanetary disks. Disk material settles into the plane perpendicular to the system's total angular momentum vector. In binary systems, this typically means disk and planet orbits align with the binary orbital plane. Finding a significantly misaligned planet challenges these standard formation scenarios. Alternative explanations invoke gravitational perturbations that modified the orbit after initial formation. Close encounters with other planets that were subsequently ejected from the system might have torqued S1's orbit to its current inclination. Long-term gravitational interactions between the planet, its host star, and the binary companion could gradually pump inclination through complex resonance effects. The inclined orbit also raises questions about long-term stability over astronomical timescales. Planets orbiting at steep angles relative to binary stellar planes experience gravitational torques that can modify both eccentricity and inclination over millions of years. These Kozai-Lidov oscillations might eventually drive orbital parameters to extremes that destroy planetary systems through stellar collisions or ejection into interstellar space. Detailed stability calculations indicate that S, one's current orbital configuration, remains gravitationally bound for billions of years despite its unusual geometry. The planet survives because it never ventures close enough to Alpha Centauri B for the companion's gravity to significantly disrupt its motion. At 2 astronomical units maximum separation from Alpha Centauri A, the planet remains safely within the primary star's gravitational sphere of influence. Alpha Centauri B currently orbits approximately 20 astronomical units from its companion. Even at closest binary approach of 11 astronomical units, the secondary star remains too distant to strongly perturb a planet orbiting within 2 astronomical units of the primary. S. One exists in a gravitational safe zone where Alpha Centauri A dominates, and the binary companion exerts only minor influence, but orbital constraints derived from just 4 observation epochs carry substantial uncertainties. 2 positive detections from 2019 and August 2024, combined with 2 null results from early 2025, provide limited information for precisely determining orbital parameters. Many different configurations remain mathematically consistent with available data. The eccentricity could range anywhere from 0.2 to 0.6 while remaining compatible with observations. Orbital periods between 18 months and 4 years fit the timing of detections and non-detections. Inclination angles from 30 to 70 degrees satisfy current constraints. Future observations will progressively tighten these ranges as additional data points constrain the allowed orbital families. The research team documented their findings in 2 peer-reviewed papers accepted for publication in the Astrophysical Journal Letters, one of astronomy's most prestigious journals. The first paper presented observational details, detection characteristics, photometric measurements, and orbital analysis. The second paper described the sophisticated image processing methodology, sensitivity characterization, and systematic error analysis required to extract marginal signals from extremely challenging data. Both papers carefully emphasized that S1 remains a candidate planet rather than a confirmed detection, despite the compelling statistical analysis. A single, robust observation epoch cannot definitively prove planetary nature regardless of detection significance. Confirmation requires tracking the object through multiple orbital phases and demonstrating that its motion follows gravitationally bound trajectories around the host star. The papers also thoroughly addressed alternative explanations that might account for the August detection without invoking an actual planet. Dust clouds represent one such possibility. Circumstellar debris from asteroid collisions or cometary activity occasionally appears as point-like signals in high-contrast coronagraphic observations before dispersing or moving beyond detection. The brightness and color characteristics of S1 remain consistent with either a planetary atmosphere or a concentrated dust cloud heated by stellar radiation. Both would emit thermal radiation at similar temperatures given their distances from Alpha Centauri A. Distinguishing between these interpretations requires additional observations at multiple wavelengths that can probe compositional differences. Could S1 be a brown dwarf rather than a true planet? These failed stars occupy the mass range between giant planets and hydrogen-fusing stars. They generate internal heat through gravitational contraction and deuterium fusion, but never achieve sustained hydrogen burning. Brown dwarfs can appear similar to planets in thermal emission observations. Mass estimates derived from S1's brightness and temperature suggest the object falls firmly in the planetary regime rather than brown dwarf territory. Brown dwarfs typically exceed 13 Jupiter masses, equivalent to approximately 4,000 Earth masses. S1 falls far below this threshold, based on current measurements, though mass uncertainties remain substantial. Could the detection represent multiple smaller objects rather than a single large planet? Swarms of asteroids or cometary debris might collectively produce signals resembling planet-sized sources under certain viewing geometries. The team considered this possibility but found it statistically less probable than the single-planet hypothesis based on observed brightness distributions and point-like morphology. The scientific community received these findings with an appropriate mixture of cautious skepticism and palpable excitement. Extraordinary claims demand extraordinary evidence, and claiming a directly imaged planet around our nearest sun-like neighbour certainly qualifies as extraordinary. The case for S1 rests on a single detection epoch, supported by theoretical arguments explaining subsequent non-detections. But if confirmation eventually arrives, S1 would simultaneously claim multiple historic records that explain the intense scientific interest despite residual uncertainty. It would become the closest exoplanet to Earth orbiting within the temperate zone of a sun-like star. The planets around Proxima Centauri lie slightly closer in raw distance, but orbit a fundamentally different stellar type. Red dwarf habitable zones and sun-like habitable zones present vastly different conditions for any worlds occupying them. It would become the nearest directly imaged exoplanet by a substantial margin. Every other directly imaged world orbits host stars at least 10 times more distant than Alpha Centauri. Proximity enables observational opportunities impossible for more remote targets. It would become the oldest directly imaged exoplanet by an enormous factor. Previous direct imaging successes uniformly targeted young stellar associations, less than 100 million years old, where planets retain the formation brightness that makes detection feasible. Alpha Centauri A has existed for billions of years, creating a planetary system as mature as our own. It would become the coldest directly imaged exoplanet. Young, hot planets dominate current detection samples because their thermal emission is orders of magnitude brighter than mature, cool worlds. S1 would open direct imaging to the cold planetary population, invisible to previous surveys. It would become the closest to its host star of any directly imaged exoplanet. Most imaged planets orbit at tens or hundreds of astronomical units from their stars, residing in frigid outer system regions far from habitable zones. S1 circles within 2 astronomical units, comparable to Mars in our solar system. These superlatives explain why astronomers remain eager to pursue additional observations Despite the challenging nature of the Alpha Centauri target and the frustrating disappearance of the initial detection, the scientific payoff from confirming S1 would justify enormous observational investment. The orbital models make specific predictions about when S1 should return to detectable positions if it genuinely exists. Based on the family of stable orbits consistent with current observational constraints, the planet should approach aphelion again in mid-2026. August 2026 represents the most probable window for redetection based on statistical analysis of allowed orbital configurations. If JWST observes Alpha Centauri A during this predicted visibility window and detects S1 near the expected position, the case for planetary confirmation becomes overwhelming. A third detection at the right location to match orbital predictions would essentially prove that a gravitationally bound object orbits our nearest Sun-like stellar neighbour. Scientists could then begin the detailed characterization studies that proximity uniquely enables. If August 2026 observations fail to detect anything despite favourable predicted geometry, the mystery deepens considerably. Either the planet follows an orbit lying outside current model predictions, requiring revision of allowed parameter ranges, or the original August 2024 detection truly was a remarkably improbable statistical fluctuation that fooled extensive testing protocols. The disappearing planet scenario illuminates fundamental limitations, constraining exoplanet detection, even with the most powerful telescope humanity has ever built. Orbital geometry creates visibility windows, interspersed with dark periods where objects move beyond detection capability, regardless of instrument sensitivity. Planets are not always observable even when they genuinely exist. For worlds orbiting distant stars, these visibility gaps represent minor scheduling inconveniences. Observers simply wait for favourable geometry and plan observations accordingly. Transit surveys operate on similar principles, catching planets only when they cross stellar faces as seen from Earth. But Alpha Centauri presents unusual complications where standard approaches fail. The extreme proximity that should make observation trivially easy instead creates challenges that force development of entirely new techniques. Visibility windows become critically important constraints, determining what information can be gathered and when opportunities arise. The saga of S1 represents scientific methodology operating exactly as designed. An improbable observation using innovative techniques revealed a tantalizing signal that passed rigorous statistical testing. Follow-up investigations using identical methods produced unexpected null results that initially seemed to contradict the original detection. Theoretical analysis demonstrated that both outcomes remain mutually consistent within a coherent physical framework. A genuine planet following certain allowed orbits would appear in August, disappear in February and April, then reappear at predicted future dates. The non-detections neither confirm nor refute planetary existence. They simply constrain orbital parameters that future observations can further refine. Science advances through exactly this iterative process of observation, analysis, prediction, and verification. The story remains incomplete. Critical chapters await writing when JWST returns to Alpha Centauri during predicted visibility windows. Whatever ultimate conclusions emerge, the process itself demonstrates how empirical investigation gradually reveals cosmic truths hidden beneath layers of uncertainty. The James Webb Space Telescope has proven that the impossible observation is now technically achievable. Alpha Centauri, untouchable target for so many decades, has finally yielded detectable signals to human ingenuity and technological achievement. Whether those signals represent a genuine planet or some alternative phenomenon, the observational barrier has been broken. The closest Sun-like star to Earth no longer hides its secrets behind impenetrable stellar glare. JWST can probe the region where habitable zone planets might orbit. Future observations will progressively reveal whatever worlds populate this nearest stellar neighborhood. The disappearing planet may reappear, or it may prove illusory upon further investigation. Either outcome advances understanding. Either result informs the search for planets around other nearby stars. The techniques developed for Alpha Centauri extend to additional targets throughout the solar neighborhood. Science proceeds one observation at a time, building understanding through accumulated evidence that eventually resolves ambiguity into knowledge. S1 currently occupies the uncertain territory between tentative detection and confirmed discovery. That uncertainty will not persist indefinitely. The universe holds answers that patient investigation will eventually extract. The question of whether planets orbit Alpha Centauri A has haunted astronomers for generations. Within the next few years, that question will receive a definitive answer one way or another. The disappearing planet mystery will be solved through the same empirical methods that created it. Close your eyes and imagine standing somewhere no human has ever been. Your feet rest on the icy surface of a moon orbiting a gas giant 4 light-years from Earth. Above your head hangs an alien sky containing wonders that would stop your heart with their beauty and strangeness. Alpha Centauri blazes overhead like a familiar friend. This yellow-white sun looks remarkably similar to the star that warms Earth, because it essentially is the same type of stellar furnace, same spectral class, same surface temperature. From your position roughly 2 astronomical units away, it delivers about 1/4 the light intensity you would experience standing on Earth. Enough warmth to feel on exposed skin, but noticeably dimmer than terrestrial noon. But something else catches your attention. A second sun hangs in your sky, brilliant orange against the black cosmic backdrop. Alpha Centauri B appears roughly as bright as the full moon seen from Earth, casting faint secondary shadows that shift position over decades as the binary pair completes their 80-year orbital dance around their common center of mass. 2 suns in one sky. Science fiction writers imagined this scenario for generations. Now we have evidence suggesting a world actually exists where this view might be real. The planet beneath your hypothetical feet defies easy description. S1 spans approximately 1 Jupiter radius across, a massive Jovian world possessing no solid surface where anything could truly stand. What appears as ground from space reveals itself upon closer approach as merely the top of an atmosphere extending thousands of miles downward into crushing pressures and temperatures. Swirling cloud bands wrap around the planetary equator in shades of tan, orange, and subtle cream. Ammonia ice crystals condense in the frigid upper atmosphere, forming high-altitude hazes that scatter starlight into spectacular twilight displays lasting hours. Storm systems larger than Earth churn through atmospheric layers, driven by heat escaping from the planetary interior and differential solar heating between equator and poles. This alien world circles Alpha Centauri A every 2 to 3 Earth years, tracing an elliptical path that carries it through dramatically varying conditions. At closest approach to its host star, the planet experiences roughly 40% more stellar irradiation than at maximum separation. These seasonal variations drive atmospheric chemistry in ways we can only simulate through computer models calibrated against Jupiter and Saturn observations. The confirmed measurements from August 2024 provide our best estimates of what this distant world actually looks like. Every number carries uncertainty, but the emerging picture reveals a planet unlike anything directly imaged before. S1 shines with a flux of approximately 3.5 millijanskis at 15.5 micrometers wavelength. This technical measurement describes how much mid-infrared light reaches JWST's detectors from the planet's direction. Converting raw flux into meaningful physical parameters requires sophisticated modeling that accounts for atmospheric composition, viewing geometry, and internal heat generation. The brightness tells us about temperature. Hotter objects emit more thermal radiation than cooler ones, according to fundamental physics principles discovered by Max Planck over a century ago. Working backward from observed flux to emitting temperature yields estimates centering around 225 Kelvin, roughly -50 degrees Celsius. This temperature makes S1 considerably warmer than Saturn, which averages only 134 Kelvin at its cloud tops. Neptune plunges to 55 Kelvin. The temperature difference arises partly from Alpha Centauri A's greater luminosity compared to our Sun. The host star pumps out roughly 50% more energy than solar output, bathing everything in its vicinity with correspondingly enhanced radiation. But stellar irradiation alone cannot account for all the observed thermal emission. Gas giants generate internal heat through processes unrelated to their host stars. Gravitational contraction slowly compresses planetary interiors, converting potential energy into thermal energy that radiates outward over billions of years. Radioactive decay of heavy elements contributes additional warmth. One likely possesses similar internal heat sources supplementing the stellar contribution. The combination of external irradiation and internal generation produces the observed temperature that places this world in a thermal regime between the ice giants of our outer solar system and the scorching hot Jupiters discovered, orbiting other stars. Mass estimates derived from brightness and temperature modelling place S1 in the Saturn class rather than the Jupiter category. For comparison, Saturn tips the scales at approximately 95 Earth masses, while Jupiter dominates at 318 Earth masses. The distinction matters because Saturn mass and Jupiter mass planets possess fundamentally different internal structures. Radius estimates fall between 1 and 1.1 Jupiter radii, meaning the planet's physical size roughly matches Jupiter despite containing less than half the mass. This combination of modest mass and substantial radius implies bulk density lower than liquid water. One would likely float alongside its solar system analogue. Low density confirms hydrogen-helium-dominated composition consistent with giant planet formation models. These planets accumulate massive atmospheres from primordial nebular gas during the earliest phases of stellar system evolution. Unlike rocky worlds built from heavier elements, gas giants form quickly by capturing lightweight gases before those gases disperse into interstellar space. The atmospheric composition of S1 remains entirely unconstrained by current observations. We detected thermal emission from the planet's outer layers, but lack spectroscopic measurements that could identify specific molecules. Future observations using JWST's spectroscopic capabilities might reveal signatures of methane, ammonia, water vapor, or other compounds expected in gas giant atmospheres. Spectroscopy works by dispersing incoming light into its component wavelengths and measuring brightness variations across the resulting spectrum. Different molecules absorb and emit radiation at characteristic wavelengths determined by their quantum mechanical properties. Identifying these spectral fingerprints reveals atmospheric constituents even for worlds too distant to visit directly. Saturn's atmosphere contains hydrogen, helium, methane, ammonia, and trace quantities of more complex hydrocarbons formed through photochemical reactions. One likely hosts a similar chemical inventory, modified by the different stellar spectrum of Alpha Centauri A and the warmer temperatures resulting from closer orbital distances. But atmospheric chemistry represents only part of what makes S1 scientifically fascinating. The planet's location within Alpha Centauri A's habitable zone creates possibilities that transform a gas giant detection into something far more profound. The habitable zone concept describes the circumstellar region where rocky planets could maintain liquid water on their surfaces. Too close to the star and water boils away into space. Too far and water freezes solid. The habitable zone marks the orbital sweet spot where temperatures permit the liquid water that terrestrial biology requires. Alpha Centauri A's temperate zone extends from roughly 1.2 to 2.5 astronomical units. Based on standard calculations, accounting for stellar luminosity and atmospheric greenhouse effects, S1 orbits within this zone, spending most of its eccentric path in regions where surface temperatures on rocky worlds could support liquid water. A world of this type obviously cannot host surface oceans or the geological processes we associate with habitability. S1 lacks solid ground where water could pool. Its crushing atmospheric pressures would destroy any Earth-like chemistry attempting to function. The planet itself is definitively uninhabitable by any reasonable definition. But giant planets rarely travel alone. Every giant planet in our solar system hosts extensive moon systems containing dozens to hundreds of natural satellites. These moons range from tiny, irregular captured asteroids to world-sized bodies with complex geology, atmospheric systems, and potentially habitable subsurface environments. Saturn possesses more than 270 known moons at current count, with new discoveries continuing as observation technology improves. The largest Saturnian satellite, Titan, exceeds the planet Mercury in diameter, while maintaining a dense nitrogen atmosphere thicker than Earth's. Liquid methane and ethane pool into seas and lakes, covering portions of Titan's frigid surface. Complex organic chemistry occurs continuously, as solar ultraviolet radiation drives reactions producing progressively larger hydrocarbon molecules. Enceladus, a much smaller Saturnian moon, conceals wonders beneath its icy exterior. A global subsurface ocean of liquid water surrounds a rocky core heated by tidal forces from Saturn's gravitational influence. Geysers erupting from fractures near the South Pole spray water vapor and organic molecules into space, creating a thin ring of particles orbiting Saturn. Scientists consider Enceladus among the most promising locations for extraterrestrial life in our solar system. Jupiter's moon Europa hosts a similar subsurface ocean, estimated at 100 kilometers depth beneath an icy shell. Tidal heating from Jupiter's massive gravitational field maintains liquid water, despite surface temperatures hundreds of degrees below freezing. Hydrothermal vents on Europa's ocean floor might provide chemical energy capable of supporting microbial ecosystems similar to those thriving near deep-sea vents on Earth. Ganymede and Callisto, two additional Jovian moons, likely contain subsurface water layers sandwiched between ice shells and rocky interiors. These ocean worlds lack the active geology of Europa, but still represent potentially habitable environments where primitive life might survive. If S1 follows the pattern established by Jupiter and Saturn, it should host an extensive satellite system containing multiple large moons and countless smaller bodies. Planetary formation models suggest moon systems arise naturally during giant planet formation as circumplanetary disks of material condense into discrete satellites. Some of these hypothetical moons might achieve conditions suitable for liquid water. A moon orbiting S1 within Alpha Centauri A's habitable zone would experience surface temperatures moderated by stellar irradiation. Unlike the frozen moons of our outer solar system, which rely entirely on internal heat to maintain subsurface oceans, moons around S1 could potentially support surface liquid water warmed by the nearby sun-like star. Imagine a tangent-like moon orbiting S1, but warm enough for liquid water rather than liquid methane. Rivers and lakes could form through familiar hydrological cycles, driven by evaporation and precipitation. Atmospheric chemistry might produce conditions recognizable to terrestrial organisms. Life could emerge through processes analogous to those that generated Earth's biosphere. This scenario transforms a gas giant detection into potentially habitable real estate discovery. We cannot observe moons around S1 with any existing technology. The angular separation between planet and hypothetical satellite would be far too small to resolve from Earth's distance, but their existence follows naturally from everything we understand about how planetary systems form and evolve. The possibility of habitable moons orbiting our nearest sun-like stellar neighbour carries profound implications for astrobiology and the search for extraterrestrial life. If S1 hosts moons, and if any of those moons achieve habitable conditions, then life might exist merely 4 light-years from Earth. 4 light-years represents a distance that future technology might actually traverse. Breakthrough Starshot and similar initiatives propose launching small spacecraft at relativistic velocities using laser propulsion systems. These probes could reach Alpha Centauri within 2 decades of launch, returning close-up observations within a human lifetime, Knowing that potentially habitable moons await arrival transforms speculative engineering into motivated mission planning. But the S1 detection carries scientific significance, extending far beyond habitability speculation. The James Webb Space Telescope achieved sensitivity levels during the Alpha Centauri observations that established new benchmarks for what direct imaging can accomplish. Consider the exozodiacal dust measurements that emerged from the same data products revealing the planet candidate. Zodiacal dust consists of microscopic particles produced by asteroid collisions and cometary activity throughout planetary systems. In our solar system, this dust forms a faint glow visible along the ecliptic plane before sunrise and after sunset. The zodiacal light results from sunlight scattering off billions of tiny particles distributed throughout the inner solar system. If Alpha Centauri A hosted a dense debris disk like those observed around many younger stars, the scattered starlight might overwhelm planetary signals or create confusing bright structures that contaminate coronagraphic observations. Dense exozodiacal emission could make planet detection impossible regardless of instrument sensitivity. The JWST observations constrained any zodiacal dust around Alpha Centauri A to levels only approximately 5 to 8 times brighter than our own solar system's zodiacal cloud. This limit represents the most sensitive measurement of exozodiacal dust ever achieved around any star other than the Sun. Previous observations of other stellar systems could only constrain debris disks to levels tens or hundreds of times brighter than solar system conditions. The Alpha Centauri data pushed sensitivity a full order of magnitude deeper than any prior constraint. For the first time, astronomers can meaningfully compare another star's dust environment to our own cosmic neighborhood. The relatively low debris levels around Alpha Centauri suggest a mature planetary system that has settled into dynamical equilibrium after billions of years of evolution. Dense debris disks typically indicate recent collisional activity in asteroid belt analogues or ongoing cometary bombardment periods. Heavy bombardment poses extinction risks for any emerging biospheres attempting to gain foothold on planetary surfaces. Finding that Alpha Centauri A lacks excessive debris provides encouraging news for habitability prospects. The system apparently avoided the catastrophic collision events that would produce bright zodiacal emission. Whatever planets or moons exist, they likely experience relatively stable conditions favorable for biological evolution over geological timescales. The contrast ratio achieved during the S1 detection deserves special emphasis for understanding what JWST accomplished. Detecting such a faint signal beside such an overwhelming glare pushes coronagraphic imaging to its fundamental limits. Imagine standing in New York City and trying to photograph a candle flame positioned beside a lighthouse beam from the vantage point of Los Angeles. The brightness difference between flame and beam approaches what JWST confronted when searching for S1 beside Alpha Centauri A. The fact that any signal emerged from such extreme contrast conditions represents a triumph of engineering and data analysis. The angular separation between planet and star measured approximately 1.5 arc-seconds during August observations. This separation corresponds to roughly 2 astronomical units at Alpha Centauri's distance. 1.5 arc-seconds may sound tiny, but it actually represents the smallest planet-to-star separation ever achieved for any directly imaged exoplanet candidate. Previous direct imaging discoveries captured planets orbiting tens or hundreds of arc-seconds from their host stars. These distant companions were easier to detect, precisely because greater separation reduced stellar contamination in the coronagraphic field. S1 challenged astronomers to push much closer toward the blinding stellar glare than any previous target attempted. The theoretical implications of S1's existence extend far beyond individual planetary detection statistics. Binary star systems were long considered hostile environments for planetary formation and survival. The gravitational interplay between stellar companions disrupts protoplanetary disk material before planets can coalesce from accumulating debris. Alpha Centauri presents a particularly challenging case. The 2 main stars approach within 11 astronomical units at closest passage, creating strong gravitational perturbations Throughout the inner system regions where terrestrial planets might form, computer simulations consistently predicted that planet formation should be suppressed or prevented entirely in such tight binary configurations. Previous theoretical work identified narrow stability zones where planets might survive despite binary gravitational influence. Close orbits within approximately 1 to 2 astronomical units of either star appeared marginally stable against long-term dynamical disruption. More distant orbits seemed prohibited by the companion star's gravitational reach. S1 apparently occupies exactly this marginal stability zone. Its eccentric orbit carries it between roughly 1 and 2 astronomical units from Alpha Centauri A, threading the needle between regions too close to the star for detection and regions too distant for gravitational stability. The planet exists precisely where theory predicted worlds might barely survive, but the orbital inclination poses additional theoretical challenges. S1 appears to orbit at roughly 50 degrees relative to the Alpha Centauri AB orbital plane. Planetary formation models generally predict that disk material and resulting planets should align with stellar rotation and binary orbital planes. Finding a substantially misaligned planet requires explanation. Several formation scenarios could produce the observed configuration. Perhaps S1 formed in an aligned orbit that was subsequently tilted through gravitational interactions with other planets that no longer exist or remain undetected. Multi-planet systems frequently experience orbital evolution that exchanges angular momentum between companions, potentially tilting inclinations over millions of years. Perhaps the planet formed elsewhere in the disk and migrated to its current location through interactions with nebular gas or remaining debris. Migration processes can modify both orbital distances and inclinations as planets plow through disk material early in system history. Perhaps the Alpha Centauri system experienced dynamical instability at some point that rearranged orbital architectures for both planets and possibly the binary stars themselves. Stellar flybys from passing systems or gravitational perturbations from the distant companion Proxima Centauri might have triggered chaotic evolution periods. Each formation scenario generates testable predictions for future observations. Finding additional planets would support multi-body gravitational interaction models. Detecting systematic variations in S1's orbit would indicate ongoing dynamical evolution. Precise characterization of the binary orbital parameters might reveal signatures of past dynamical settling. The broader implications ripple throughout galactic planetary science. Approximately half of all Sun-like stars in the Milky Way reside in binary or multiple stellar systems. If planets can form and survive around Alpha Centauri, despite its tight binary companion, then similar worlds might populate countless other binary systems throughout the galaxy that were previously dismissed as hostile to planetary formation. Conservative estimates suggest roughly 200 billion stars populate our galaxy. If half exist in binary configurations, 100 billion binary systems await investigation. Even if only 10% of these binaries host planets, 10 billion worlds orbit binary stellar pairs throughout the Milky Way. Some fraction of these might occupy habitable zones where conditions support liquid water and potentially life. Adding binary star planets to the galactic census dramatically increases estimates of potentially habitable real estate. Single star systems were already expected to host billions of Earth-like worlds based on Kepler mission statistics. Binary planetary populations might double or triple total habitability estimates, fundamentally reshaping our understanding of how common life-supporting environments might be throughout the cosmos. The sensitivity limits achieved during Alpha Centauri observations also constrain what types of planets we can confidently exclude from the inner system. The detection threshold established by these observations would have revealed any Jupiter-mass planets orbiting beyond approximately 2 astronomical units from Alpha Centauri A. The absence of such detections suggests the inner system lacks additional giant planets in the surveyed region. This null result carries important implications for smaller worlds that remain below direct imaging detection limits. Giant planets gravitationally influence the orbits of smaller companions, potentially destabilizing rocky worlds through resonance interactions or close encounters. A system containing numerous giant planets leaves less dynamically stable phase space for potentially habitable terrestrial planets. Finding only one modest gas giant in the Alpha Centauri, an inner system leaves substantial orbital real estate potentially available for smaller rocky worlds. Earth-sized planets could orbit closer to the star within the inner habitable zone without gravitational harassment from giant companions. Such worlds remain far below current detection thresholds, but might reveal themselves through alternative observation methods. Radial velocity surveys measure stellar wobbles induced by planetary gravitational tugs. Massive nearby planets create larger wobbles than distant, lightweight worlds. Earth-mass planets at Earth-like orbital distances produce stellar velocity variations below 1 meter per second, challenging but not impossible for modern precision spectrographs to detect. Transit photometry watches for periodic brightness dips when planets cross stellar faces as viewed from Earth. The geometric probability of observing transits depends on orbital alignment, with closer planets more likely to show transits than distant ones. Alpha Centauri A has been monitored for transits without positive detection, constraining but not eliminating the possibility of close-in rocky planets. Astrometric measurements track stellar position shifts caused by planetary gravitational influence. Future, extremely precise astrometry might detect Earth-mass planets around nearby stars, including Alpha Centauri. The Gaia spacecraft has already begun constraining planetary populations through astrometric techniques that will continue improving as mission data accumulates. Each detection method probes different planetary populations with different strengths and limitations. Direct imaging revealed S1 because it was large enough and distant enough from its star to emerge from coronagraphic suppression. Smaller planets closer to the star await detection through complementary techniques operating on different physical principles. The psychological weight of finding a planet around our nearest Sun-like stellar neighbour transcends cold scientific statistics. For generations, Alpha Centauri has occupied a unique position in human cosmic imagination. This nearby stellar system represents the first realistic destination for interstellar travel, the closest target where other Sun-like conditions might support life, the cosmic neighbour we have wondered about since first understanding that stars are distant suns. Science fiction writers imagined expeditions to Alpha Centauri long before anyone knew whether planets awaited arrival. Stories placed alien civilizations, habitable worlds, and cosmic wonders around these nearby stars without any observational evidence supporting such speculation. The system became shorthand for humanity's interstellar aspirations, precisely because of its proximity and Sun-like stellar characteristics. Now we possess evidence suggesting at least one world actually circles our nearest Sun-like star. The speculation has transformed into observation. The imagined destination has revealed itself through painstaking technical achievement. Whatever secrets Alpha Centauri holds, humanity has finally developed tools capable of extracting them from the blinding stellar glare. Whether S1 ultimately achieves confirmed planet status or fades into statistical uncertainty, the detection demonstrates that Alpha Centauri's planetary system can be explored from Earth. The barriers that protected this system's secrets for all of human history have finally yielded to ingenuity, persistence, and engineering excellence. A Saturn-mass world may orbit in the habitable zone of our nearest cosmic neighbour. That world may host moons where liquid water flows beneath alien skies illuminated by two suns. Life may have emerged on those moons through processes paralleling terrestrial biological evolution. Or the system may prove barren, devoid of the conditions necessary for biology. Either answer advances human understanding. Either outcome informs the search for life elsewhere in the cosmos. The James Webb Space Telescope has cracked open a door that remained sealed throughout all prior human history. What lies beyond that door awaits future observations to reveal. The August 2026 observation window approaches like a verdict, awaiting delivery. Somewhere in the vast emptiness between now and then, a Saturn-mass world may or may not be tracing an eccentric ellipse around the third brightest star in our night sky. The planet either exists or it does not. The universe already knows the answer. We simply lack the observations to extract that truth from cosmic silence. The orbital models make specific predictions. If S1 is real and follows the family of stable orbits consistent with current detections, it should return to favorable positions where JWST's coronagraph achieves sufficient sensitivity for detection. The planet's elongated path will carry it back toward aphelion, emerging from the stellar glare that has hidden it since August 2024. Scientists have already begun planning for this critical observation window. Telescope time requests are being prepared. Data analysis pipelines are being refined based on lessons learned from previous attempts. The entire astronomical community watches with anticipation as the predicted reappearance date approaches. If S1 appears at the expected position, the case for planetary confirmation becomes overwhelming. 3 independent detections spanning 7 years, including the 2019 ground-based hint, the 2024 JWST discovery, and the 2026 confirmation, would definitively establish orbital motion consistent with gravitational binding to Alpha Centauri A. No statistical fluctuation or background contamination could produce such a coherent pattern across multiple epochs and instruments. If S1 fails to appear despite favorable predicted geometry, the mystery deepens considerably. Either the orbital models require revision to accommodate configurations that keep the planet hidden longer than expected, or the original detection truly was an extraordinarily improbable false positive that fooled every statistical test designed to catch such errors. Either outcome advances scientific understanding. Confirmation opens unprecedented opportunities for detailed characterization of our nearest planetary neighbor. Refutation eliminates a candidate while refining techniques for future searches. Science progresses through both positive and negative results when interpreted carefully. But the implications of the S1 detection extend far beyond whether this particular candidate achieves confirmed status. The James Webb Space Telescope has opened a door that cannot be closed regardless of what lies immediately beyond the threshold. Direct imaging of mature planets around Sun-like stars at close angular separations is now demonstrated possible. The most powerful space telescope ever constructed has proven equal to tasks its designers never imagined when they drafted specifications decades ago. Consider what becomes possible if 2026 observations confirm S1 as a genuine planet orbiting Alpha Centauri A. The scientific return from a verified detection would reshape multiple fields of astronomical research in ways that ripple outward for generations. Atmospheric characterization becomes achievable for the first time on a mature gas giant orbiting a Sun-like star. With repeated observations across different orbital phases, astronomers can analyze how S1's thermal emission varies as its eccentric path carries it between perihelion and aphelion. These brightness variations encode information about atmospheric composition, vertical temperature structure, cloud deck properties, and global weather patterns. When S1 approaches closer to Alpha Centauri A, increased stellar heating should drive atmospheric dynamics and alter chemical equilibrium states. When it retreats toward aphelion, cooling should produce different spectral signatures as temperature-sensitive molecules respond to changing conditions. Monitoring these seasonal variations provides insights impossible to obtain from single-epoch observations of more distant exoplanets. No other known planetary system offers comparable opportunity for detailed atmospheric study of a mature gas giant. Most directly imaged exoplanets orbit young stars, where formation heat dominates thermal emission. Their atmospheres reflect primordial conditions rather than the evolved states characterizing billion-year-old worlds like those in our solar system. S1 would provide the first directly comparable case study for understanding how gas giant atmospheres behave after billions of years of evolution. Spectroscopic observations could identify specific molecules in S1's atmosphere by detecting their characteristic absorption and emission features. Methane, ammonia, water vapor, and various hydrocarbon compounds should produce measurable signatures at mid-infrared wavelengths accessible to JWST. Comparing these detections against solar system gas giants would reveal how atmospheric chemistry depends on stellar irradiation, spectra, orbital distance, and planetary mass. Orbital dynamics become measurable with increasing precision as observations accumulate across multiple years. Each detection epoch constrains the allowed orbital parameter space, progressively eliminating configurations inconsistent with observed positions. Long baseline observations spanning a decade or more might achieve sufficient precision to detect subtle gravitational perturbations from additional unseen planets sharing the system. If other worlds orbit Alpha Centauri A, their gravitational influence would cause S1's observed positions to deviate slightly from pure two-body Keplerian motion. These perturbations appear as systematic residuals when comparing predicted and observed locations. Detecting such signatures would reveal hidden planetary companions too small or poorly positioned for direct detection. The orbital evolution itself provides tests of theoretical models predicting how planets survive in binary stellar environments. One's unusual inclination and eccentricity should produce measurable precession as gravitational torques from Alpha Centauri B slowly rotate the orbital plane and perihelion direction. Tracking these changes over decades tests whether theoretical stability calculations correctly predict long-term dynamical behavior. Moon searches become feasible as next-generation telescopes approach completion. While JWST lacks resolution to detect satellites around S1, future extremely large ground-based telescopes might achieve the angular precision required to identify large moons orbiting the planet. A tangent-sized satellite would produce detectable signals if it orbits far enough from S1 to resolve as a separate source. The extremely large telescope under construction in Chile's Atacama Desert will possess a primary mirror 39 meters in diameter when it achieves first light. This enormous aperture exceeds any existing optical telescope by a factor of 4, providing correspondingly improved angular resolution and light-gathering capability. Its coronagraphic instruments will push contrast ratios and inner working angles beyond current space-based performance. The 30-meter telescope, planned for Mauna Kea in Hawaii, offers similar revolutionary capabilities through a segmented primary mirror, rivaling the ELT in effective aperture. The giant Magellan telescope, also under construction in Chile, combines 7 8.4-meter mirrors into a coherent array with 25-meter equivalent diameter. Each facility represents a quantum leap in observational capability that will transform exoplanet science. Within a decade, these instruments will observe Alpha Centauri with sensitivity exceeding JWST's current performance by substantial margins. If S1 is real, ground-based telescopes will track its orbital motion with sub-milliardsecond precision impossible from space-based platforms. If additional planets exist in the system, larger apertures and improved coronagraphs will detect them where current instruments see only empty space. Interstellar mission planning gains a concrete target that transforms speculative engineering into focused development. Breakthrough Starshot and similar initiatives have proposed launching gram-scale spacecraft toward Alpha Centauri at relativistic velocities using ground-based laser propulsion systems. These visionary concepts imagine pushing tiny probes to 20% of light speed, enabling arrival at our nearest stellar neighbor within approximately 21 years of launch. Such missions seemed almost pointlessly speculative when we knew nothing about what awaited at the destination. Why invest billions of dollars and decades of effort to visit a stellar system that might prove entirely barren? The uncertainty surrounding Alpha Centauri's planetary population undermined enthusiasm for interstellar mission concepts. Knowing that planets exist changes the calculation fundamentally. Mission designers can incorporate specific objectives based on known planetary characteristics. Observation strategies can target predicted orbital positions derived from increasingly refined models. Instrument specifications can emphasize measurements most relevant to understanding what the system actually contains. The possibility of habitable moons around S1 further amplifies mission motivation. If a tangent-like satellite orbits within the habitable zone, close-up observations could search for biosignatures impossible to detect from Earth's distance. Atmospheric spectra might reveal oxygen, methane, or other gases indicating biological activity. Surface imaging might show liquid water features or vegetation signatures. The scientific payoff from such discoveries would justify almost any conceivable mission cost. Even without biological detections, close-range planetary observations would revolutionize comparative planetology. We currently know gas giants only from the 4 examples in our solar system, plus distant exoplanets observed through limited techniques. S1 would provide a 5th detailed case study formed in an entirely different stellar environment. Comparing its atmospheric structure, magnetic field configuration, satellite system, and ring properties against Jupiter and Saturn would reveal how these characteristics depend on formation conditions and evolutionary history. The broader impact on exoplanet science proves equally profound regardless of S1's ultimate confirmation status. The detection demonstrates that mature planetary systems can be characterized through direct imaging when telescopes push beyond nominal design specifications. This success encourages similar attempts at other nearby stellar targets that were previously considered impractical. Tau Ceti lies approximately 12 light-years from Earth, roughly 3 times more distant than Alpha Centauri, but still close enough to enable direct imaging attempts with current technology. This sun-like star has already yielded radial velocity detections, suggesting several planetary candidates orbiting at various distances. Some of these suspected worlds might be massive enough and positioned favorably enough for coronagraphic detection using techniques proven at Alpha Centauri. Epsilon Eridani orbits at 10.5 light-years distance, close enough for detailed investigation despite being more than twice as far as Alpha Centauri. This relatively young star, aged only several 100 million years, possesses a confirmed debris disk, suggesting active dynamical evolution and possible ongoing planet formation. Direct imaging attempts might capture young planets still glowing brightly from formation heat, appearing far more prominently than the cool, mature world detected around Alpha Centauri A. 70 Ophiuchi presents another intriguing binary system target at roughly 16 light-years distance. The 2 orange dwarf stars orbit each other with a period of roughly 88 years, creating dynamical conditions somewhat similar to the Alpha Centauri configuration. If planets can survive around Alpha Centauri A, perhaps similar worlds populate the 70 Ophiuchi system awaiting detection. Sirius presents challenges remarkably similar to Alpha Centauri due to its extreme brightness and binary companion. At 8.6 light-years, this brilliant stellar system ranks as the brightest star in Earth's night sky. Its white dwarf companion, Sirius B, represents the remnant core of a star that previously passed through red giant evolution. Any planets surviving that violent stellar death might orbit in unusual configurations worth investigating. Each nearby system offers unique scientific opportunities if direct imaging techniques can be extended to new targets. The Alpha Centauri success provides both confidence that such observations are achievable and specific methodology for addressing the technical challenges bright nearby stars present. The blind offset technique, the reference star subtraction, the sophisticated data reduction pipelines all transfer directly to other targets with appropriate modifications. The implications extend beyond individual planetary system characterization to fundamental questions about life in the universe that have haunted human consciousness since we first understood that stars are distant suns. The Drake equation famously attempts to estimate the number of technologically capable civilizations that might exist in our galaxy at any given time. Frank Drake formulated this probabilistic framework in 1961 as a way to organize thinking about extraterrestrial intelligence. The equation multiplies together factors including the rate of star formation, the fraction of stars hosting planets, the fraction of planets where life emerges, and subsequent terms describing intelligence and technology development. Before the exoplanet revolution began in the 1990s, astronomers debated intensely whether planets existed around most stars or only rare stellar configurations. Some theoretical models suggested planetary formation was common. Others argued that our solar system might represent an unusual outcome from processes that typically failed to produce worlds. The discovery of thousands of exoplanets through transit surveys, radial velocity measurements, and direct imaging settled this debate decisively. Planets are ubiquitous throughout the galaxy. Nearly every star possesses at least one planetary companion. The term in Drake's equation representing planetary frequency approaches unity. Worlds are everywhere, but the Drake equation terms involving life remained purely speculative despite planetary abundance. We possess exactly one example of life emerging on a planet. That single data point, Earth, tells us almost nothing about how common biological genesis might be throughout the cosmos. Life might arise inevitably whenever conditions permit, or life might require such improbable coincidences that Earth represents a singular miracle in an otherwise sterile universe. Finding potentially habitable environments around our nearest Sun-like stellar neighbour changes how we approach this uncertainty. If Alpha Centauri hosts moons where liquid water could exist, the closest stellar system we can meaningfully study offers opportunities that more distant targets cannot match. A spacecraft travelling at 20% of light speed would reach Alpha Centauri in approximately 21 years after launch. Adding transmission time for returning data to Earth extends the total round trip to roughly 25 years. Assuming communication signals travel at light speed, within a single human lifetime, we might receive close-up observations from another stellar system capable of resolving questions about habitability that remain forever ambiguous from Earth-based telescopes. No other target allows such prompt investigation with foreseeable technology. The next nearest Sun-like stars after Alpha Centauri lie 2 to 3 times more distant, extending mission timelines to 50 years or longer. Barnard Star and Wolf 359 are closer in raw distance, but are red dwarfs fundamentally different from our Sun. Epsilon Eridani and Tau Ceti offer sun-like conditions but require correspondingly longer travel times. Alpha Centauri represents humanity's only realistic destination for interstellar probes within the coming century. Everything about this system matters enormously precisely because we might actually visit it within timescales relevant to human planning and ambition. The detection of S1, even as an unconfirmed candidate requiring additional verification, focuses engineering attention on what future missions might accomplish. Propulsion system designs can optimize for the specific distance and velocity requirements of Alpha Centauri trajectories. Communication system architectures can account for the precise signal propagation delays involved. Scientific instrument packages can emphasize measurements most relevant to characterizing known planetary targets. This focusing effect accelerates technological development by providing concrete objectives rather than abstract possibilities. Engineers work more effectively when they know exactly what problems require solving. The difference between designing a mission to somewhere versus designing a mission to a specific known destination with characterized targets produces dramatically different engineering outcomes. But we need not wait for interstellar probes to advance understanding of Alpha Centauri and similar nearby systems. Ground-based telescope facilities approaching completion will revolutionize exoplanet observations from Earth's surface within the coming decade. The extremely large telescope represents the flagship of this new generation. Its 39-meter primary mirror will collect more light than all existing large telescopes combined. Adaptive optics systems will correct atmospheric distortion in real time, achieving angular resolution exceeding space-based observatories despite Earth's turbulent atmosphere. First light is anticipated before 2030. The ELT's coronagraphic instruments will achieve contrast ratios and inner working angles, pushing well beyond current capabilities. Planets currently hidden in stellar glare will become detectable, Atmospheric spectra, currently too faint to measure, will yield chemical compositions. The Alpha Centauri system that JWST observed with such difficulty will become a routine target for detailed characterization. The 30-meter telescope and Giant Magellan Telescope offer complementary capabilities from different geographical locations. Having multiple extremely large facilities distributed across Earth's surface enables continuous monitoring of interesting targets and provides redundancy against weather interruptions or technical failures. The combined observational power of this telescope generation exceeds anything previously available by enormous margins. Within 15 years, these instruments will observe Alpha Centauri with sensitivity vastly exceeding JWST's current performance. If S1 is real, ground-based telescopes will refine its orbital parameters to extraordinary precision. If additional planets exist at smaller separations or lower masses, the new facilities will find them. If atmospheric biosignatures exist on hypothetical moons, spectroscopic observations might detect them. The James Webb Space Telescope itself continues improving as operations teams optimize performance based on accumulated experience. The Alpha Centauri observations taught valuable lessons about handling extreme brightness targets that inform better strategies for future campaigns. New data reduction algorithms extract additional sensitivity from existing hardware through more sophisticated treatment of systematic noise sources. The telescope that seemed pushed beyond its fundamental limits during the August 2024 observations may find additional capability through operational refinements and analysis improvements. The detection threshold achieved then might not represent the ultimate performance flaw. Future observations might reach even fainter signals at even smaller separations through continued technical development. Future space observatories specifically designed for exoplanet imaging are advancing through development pipelines. The Habitable Worlds Observatory, recommended by the most recent Astronomy and Astrophysics Decadal Survey, would directly image Earth-like planets around nearby stars for the first time. This ambitious mission concept incorporates lessons learned from JWST, Roman, and ground-based coronagraph demonstrations. The technology pathfinder observations achieved at Alpha Centauri directly inform Habitable Worlds Observatory designs. The contrast ratios required, the angular separations involved, the systematic noise sources encountered all provide real-world data for engineering teams working on next-generation instruments. Success at Alpha Centauri validates approaches that might otherwise seem optimistically theoretical. The Nancy Grace Roman Space Telescope, launching in the mid-2020s, includes a coronagraph technology demonstration that will test starlight suppression techniques beyond any currently operational system. While Roman's primary science involves wide-field surveys rather than targeted exoplanet imaging, its coronagraph will prove concepts essential for subsequent dedicated missions. Each technological advance in this progression brings humanity closer to answering perhaps the most profound question our species has ever posed. Are we alone in the universe? The search for life beyond Earth drives an enormous fraction of modern astronomy, planetary science, and astrobiology research. Every exoplanet detection contributes data points toward eventually resolving this cosmic mystery. Finding planets around Alpha Centauri advances this grand endeavor more directly than perhaps any other conceivable discovery. The proximity that makes observation so challenging also makes investigation so valuable. Whatever we learn about the nearest stellar system applies most directly to understanding our own cosmic neighborhood and the prospects for life within reach of future exploration. But the S1 detection carries philosophical weight, extending beyond scientific investigation into questions about human identity and cosmic significance that have occupied thinkers throughout recorded history. For all of human existence until remarkably recently, the stars represented unreachable lights decorating the night sky. Ancient cultures created elaborate mythologies around stellar patterns that seemed eternal and unchanging. The cosmic sphere appeared fundamentally different from the terrestrial realm, where human lives unfolded through birth, struggle, and death, Modern astronomy, beginning roughly 4 centuries ago, revealed stars as distant suns, nuclear furnaces generating light through thermonuclear fusion processes, operating according to the same physical laws governing earthly phenomena. The same quantum mechanics explaining laboratory spectroscopy also explains stellar atmospheres billions of miles away. This realization unified the cosmos under comprehensible natural law rather than supernatural mystery. The exoplanet revolution, beginning 3 decades ago, extended this unification to planetary systems, worlds similar to and vastly different from those orbiting our sun circle countless other stars throughout the galaxy. The gravitational collapse, disk formation, and planetary accretion processes that created Earth operate everywhere stars form. Rocky planets, gas giants, ice worlds, and exotic configurations unknown in our solar system populate stellar systems throughout the observable universe. These discoveries transformed human understanding of cosmic organization. We learned that planets are common, perhaps nearly universal around stars capable of hosting them. Statistical extrapolations suggested billions of potentially habitable worlds scattered throughout the Milky Way alone. The loneliness implied by cosmic vastness softened somewhat, with the recognition that countless other worlds might support the emergence of life and perhaps intelligence. But exoplanet statistics remained abstract. We knew planets existed in aggregate without knowing details about specific individual worlds around particular nearby stars. The third brightest star in the sky remained a question mark despite centuries of telescopic observation. Our nearest sun-like stellar neighbor guarded its planetary secrets behind impenetrable glare. Now we detect a specific planet around an individual nearby star. The abstraction of exoplanet population statistics collapses into concrete reality. That particular point of light visible tonight from southern latitudes apparently hosts its own planetary system, including at least one gas giant world orbiting within the habitable zone. This personalization of cosmic knowledge transforms how we understand our relationship to the universe. We are not merely observers cataloguing anonymous stellar populations across unimaginable distances. We are neighbors in a cosmic community. The 4.37 light-years separating Earth from Alpha Centauri seem somehow less isolating when we know what awaits across that gulf. The distance remains enormous by human standards. The travel time prohibits visitation with any currently operational technology. Communication delays render conversation impossible even if recipients existed to receive messages. But the gulf has transformed from infinitely vast in practice to merely very large in principle. The barrier is technological rather than fundamental. Nothing in physics prevents eventual crossing. The challenge lies in engineering rather than impossibility. Science fiction writers have imagined Alpha Centauri as humanity's first interstellar destination for generations. Stories placed alien civilizations, habitable worlds, mysterious phenomena, and cosmic wonders around these nearby stars without any observational evidence supporting such speculations. The system became shorthand for interstellar aspiration, precisely because proximity suggested achievability. Now those fictional speculations edge toward observational reality. We cannot yet confirm alien civilizations or habitable moons, but we can confirm that at least one planetary candidate orbits our nearest sun-like stellar neighbor. The imagined destination has begun revealing its actual nature through the patient accumulation of photons captured by instruments stationed 1 million miles from Earth. The universe reveals its secrets gradually to species that develop tools capable of asking questions and patience capable of awaiting answers. Humanity has wondered whether planets orbit Alpha Centauri since we first understood that stars might host worlds like our Sun hosts Earth. That wondering persisted through centuries of technological development that progressively improved our ability to seek answers. The James Webb Space Telescope represents the culmination of decades of effort by thousands of scientists and engineers who designed, built, tested, launched, and now operate the most powerful astronomical observatory ever constructed. Their work has produced the first meaningful answer to questions that haunted previous generations of astronomers who lacked the tools to investigate. That answer remains provisional. Confirmation awaits future observations during predicted visibility windows. The 2026 campaign will either verify S1's existence or deepen the mystery of its apparent disappearance. Either outcome advances understanding while generating new questions for subsequent investigation. But regardless of what 2026 reveals, the James Webb Space Telescope has proven that Alpha Centauri's planetary system can be explored from Earth. The observational barriers protecting this system's secrets throughout all prior human history have finally yielded to ingenuity, persistence, and engineering excellence. Whatever worlds populate our nearest stellar neighborhood, we now possess tools capable of detecting them. The fireflies hovering beside the cosmic searchlight have finally revealed themselves to patient observers willing to push technology beyond its nominal design parameters. The closest sun-like star to Earth no longer maintains perfect privacy. Its planetary companions, whether one or many, whether confirmed or merely suspected, have begun emerging from the stellar glare that hid them since the first humans looked upward and wondered. A gas giant world may orbit in the habitable zone of Alpha Centauri A. That world may host moons where liquid water pools beneath alien skies, illuminated by two suns tracing their slow orbital ballet. Life may have emerged on those moons through processes echoing what occurred on Earth billions of years ago. Or the system may prove barren, a collection of sterile worlds devoid of the conditions biology requires. Either answer represents profound knowledge worth the effort required to obtain it. Either outcome informs humanity's understanding of our place in a cosmos that increasingly reveals itself as filled with worlds beyond counting. The James Webb Space Telescope has cracked open a door sealed throughout all previous human existence. What lies beyond awaits the patient accumulation of observations that will eventually resolve mystery into knowledge. The August 2026 observation window approaches. The universe already knows whether S1 will reappear at the predicted position or remain hidden despite favourable geometry. We simply await the light that will carry that answer across 4.37 light-years of emptiness to detectors waiting in the darkness beyond Earth's atmosphere. Whatever that light reveals, the search will continue. Other nearby stars await similar investigation. Other planetary systems will yield their secrets to telescopes even more powerful than JWST. The cosmic neighborhood that seemed forever unknowable has begun transforming into territory we can systematically explore and eventually understand. The impossible observation has been achieved. The nearest sun-like star has revealed at least one planetary candidate to instruments pushed beyond their design limits by determined scientists who refused to accept that some targets were simply too difficult. That achievement cannot be reversed regardless of what future observations reveal about S1 specifically. Humanity has looked into Alpha Centauri and discovered that planets almost certainly orbit there. The exact number, masses, and configurations await determination through continued investigation. But the fundamental question that motivated generations of astronomers has finally received its answer. Our nearest stellar neighbour hosts worlds of its own. The cosmic loneliness that Earth might have experienced as the only inhabited world in a vast and sterile universe grows slightly less acute with every planetary detection around nearby stars. Whatever S1 ultimately proves to be, the detection represents a milestone in human understanding that future generations will remember as the moment Alpha Centauri finally yielded to our persistent wondering. The stars are not merely lights in the sky. They are suns with planets of their own, and the closest ones are finally revealing themselves to observers patient and clever enough to seek them out. That changes everything about how we understand our place in the cosmos and our prospects for eventually finding others who share this galaxy with us.